Namaskara students, welcome to Karnataka KCET and boards, and today we are going to do solution chapters. We are going to do the previous year questions as well, and from my handwritten notes we are going to do the solution chapter complete. I am not going to miss even a single thing from this chapter. So now let us start this without wasting any time. But before that, don't forget to like this video, and in the end I want your comments in the comment section, and also share this video among your friends. So let us start the session. Okay, so starting with the solution chapter, first thing is what exactly is a solution. So solution are homogeneous mixture. That means homogeneous mixture means mixtures are of two types, right? One is homogeneous, one is heterogeneous. Homogeneous mixture is that in which you have the uniform composition, right? This is homogeneous mixture, and this is heterogeneous mixture. Heterogeneous mixture. Homo means one and hetero means many. So here there is uniform distribution of the constituents. Okay, uniform distribution. Ma'am, what do you mean by uniform distribution? So guys, it's very simple. That for example, what is a uniform? When everyone is wearing the same kind of dress, that is a uniform. So in a uniform composition, like when you are dissolving sugar into the water, right, what you are thinking that when you take one spoon and take a sip of that, then that will have the same amount of sugar as that will be in the last one, right, if the sugar is fully dissolved in the water. But if you talk about you're dissolving you're dissolving sand, soil into the water, you will observe that the sand is settling down in the bottom, and the upper part has less soil but the bottom part has more soil. So here you can say that this is non-uniform distribution. This is non-uniform distribution. Non-uniform distribution. So in this non-uniform distribution, what we are going to talk about is homogeneous mixture of two or more than two compounds, right? When you are having two compounds, that is called binary, right? When you are having two compounds, okay. So when you are having two compounds, that is called as binary, right? Two is called as binary. When you are having three compounds, that is called as ternary. When you have four compounds, that is called as quaternary. Quaternary, right? But in this chapter, we are only going to focus on binary solutions, right? Only binary solution, which is having one solute and one solvent. Now, what is a solute? A solute is that one. A solute is that one which is less in amount. Which is less in amount, right? But a solvent is the one which is more in amount. A solvent is the one which is more in amount. For example, you are adding in the water, you are adding sugar, right? Now sugar is small in amount, right? You have a full glass of water and you're adding maybe 2, maybe 3 spoons of sugar. So sugar is less in amount, so that is your solute, and water becomes your solvent. By the way, water is a universal solvent. Mostly you will see water as the solvent, right? Next thing is type of solutions. So for binary solutions only we are talking about, which has one solute and one solvent. Which has one solute and one solvent, which is made up of solute plus solvent. Now, binary solutions are of three types. One is gaseous, liquid and solid solutions, right? So, gaseous solution means in which gas is the solvent, right? Here you can write here directly that gas is solvent. Gas is the solvent here. Here gas is the solvent. If you talk about liquid solutions, here liquid is the solvent. Liquid is solvent. But if you talk about gaseous solutions, here the more amount will be of gases. So gas is the solvent. Gas is the solvent. Now in your NCERT, a very interesting table is given, and from there also the question can be asked. This is the table. You might have studied this table as well in your lower classes. So just go through this table once. What they are saying is that Gaseous solution is in which solvent is gaseous, solute can be gas, liquid or solid, and here examples are mentioned to you, right? Then liquid is the solvent, gas, liquid, solid can be the solute, and these are the examples. Now, if solid is the solvent, gas, liquid, solid can be the solute, and here are the examples. If I pick any of this, for example, let us talk about an example of gas as the solvent and solid as the solute. So example is camphor in nitrogen gas. So when in the nitrogen gas you add a little bit of camphor, that is called a solid, is added in a large amount of gas, that is called a gaseous mixture. Okay, gaseous solution. Understood? Now you can go through this very important table from your NCERT only. Next is concentration terms. So in solution chapters, we will firstly study the concentration terms. You must have studied this in some basic concepts of chemistry as well, right? So I'm going to recap that thing for you. So guys, there are three main important concentration terms for you: molarity, molality, and normality. Okay, so if you talk about molarity, right, in molarity and molality there is difference of R and L, right? So here in molarity we take number of moles of solute divided by the volume of solution in milliliters. If we take this in milliliters, this will be multiplied by 1000. If we don't multiply this by 1000, then this will be taken in liters. Okay, so you can learn one definition, that in this case the volume of the solution is in liters, number of moles of solute divided by volume of solution in liters. If the volume of solution is in milliliters, then this will be multiplied by 1000, right? That is molarity. So you can remember this by V RAT. It all cricket fans out there. So V is your volume and R is your molarity. R molarity. Okay. Now molarity is temperature dependent. As you can say, molarity changes with change in the temperature because volume depends on the temperature. See, all the concentration terms which involves volume, they will depend on the temperature, right? They will definitely depend on the temperature. If they ask you the relation of molarity and temperature, molarity decreases with the rise in temperature. They are inversely proportional to each other. For molarity, the symbol is capital M. That means molarity is inversely proportional to temperature, right? Okay, this you can understand because 3 questions, and this will be, you can just learn this with the help of Virat, right? So this is volume, this is volume, this is molarity, and this is temperature dependence. This is temperature dependence, that it is definitely dependent on the temperature, right? Okay, next is molality. Now if you talk about molality, this case you don't have volume, rather you have weight of not solution, weight of solvent, right? Now this is a very important thing. Let me correct it here. If your mass of solvent is in grams, then this will be multiplied by 1000. But if it is not in grams, it is given in kilograms, then this thing will not be there. Then this will not be multiplied by 1000. Okay, you just need to remember this particular thing. Now I am writing the formula with multiplication of 1000. That's why I have written mass of solvent in grams. Okay. Now next is normality, and this is independent of the temperature. It does not include any volume, so it is independent of the temperature. Third one is normality, right? So now normality, a very important concept of physical chemistry. Now guys, normality is somewhat like molarity only, just that in the molarity you have number of moles of solute, and here you have number of gram equivalent of solute, right? Here you have number of gram equivalent of the solute, right? Understood this thing? Number of gram equivalent, right? Now ma'am, what is this number of gram equivalent? Ma'am, what is the difference between number of moles and number of gram equivalent, right? In detail we have learned this in some basic concepts of chemistry, like, but I am thinking that you don't you can't recall that, so that's why I am teaching you this again here, right? That number of gram equivalents is equals to mass of solute divided by equivalent mass. Okay, tell me what is number of moles. Number of moles is equals to mass of solute divided by molar mass. Number of gram equivalents will be equals to equivalent mass, right? Instead of molar mass, if you put equivalent mass, that will be calculated, that will be the calculation of number of gram equivalents, right? Number of gram equivalents. So what is equivalent mass? Equivalent mass is very simple. When you divide your molar mass with the valency, that means you can write this here, that equivalent weight is equals to molar weight divided by the n factor. Divided by n factor. This you can write here. Right? Equivalent weight is equals to molar weight divided by n factor. N factor is nothing but it is valency. Right? So you can write here also n factor is nothing but it is valency. Right? So mass of solute multiplied by the valency. Because here mass, molar mass divided by the valency, it will be na. So it will be weight of solute divided by molar mass of solute multiplied by the n factor or the valency. That will be the calculation of normality, right? Okay. Now, next very important and very useful concentration term in this chapter is mole fraction. So, mole fraction is basically, this is represented by this chi. If you have maybe two components, then I'll say if you want to calculate the mole fraction of first component, then it will be number of moles of that component divided by total number of moles. If you want to calculate mole fraction of second components, that will be number of moles of that component divided by total number of moles. Now, you are saying that, ma'am, I have infinity number of, I have maybe 10 components. So, mole fraction of third component is equals to number of moles of third component divided by total number of moles of those 10 components, n3 plus n4 and so on up to n10. You have to add all the number of moles of that component. That is going to be your mole fraction of third component. Okay, that is going to be the mole fraction of third component. Now guys, next thing is, now you have done the mole fraction of third component as well. This is the mole fraction of first and second component. Now the thing is that mole fraction of all the components. Mole fraction of all the components. Now we have two components here. That will be equals to unity. I have 10 components here. So the mole fraction of all the 10 components will be equals to unity, so on up to 10. That will be equals to unity. That is called your mole fraction. Okay, understood? Yes, everybody. So we have written it here. It is number of moles of one component to number of moles of all the components present in the solution itself. Right? Now, one thing to remember here throughout this chapter, just remember one thing, that whenever I am writing 1, because I am talking about binary solutions here. If I am representing, so it's not that always you have to do this. It's just that if you do this, it will make it easy for you to understand and learn the formulas. Right? So I am representing, and mostly in most of the books you will see this, that 1 will be representation of the solvent and 2 will be the representation of the solute. 2 will be the representation of the solute. Okay? Yes. Now that's why we have written W2 M2, because 2 is representing the solute. Right? Next is mass percentage. Now what is mass percentage? Very simple thing. Mass percentage is basically, you always have to do this thing, because it is percentage, it will be multiplied by 100. Mass percentage will always be solute by solution. Solute by solution. So there are three kind of mass percentage, these three kind of percentages that you have. First is weight by weight percentage, mostly we will use this. Next is weight by volume percentage. 3 need. You have 4 kind of percentages here, right? Third, and this is the fourth one. Okay. Just writing, wait a minute. I'm just going to write it again, right? So 4 kind of percentage that we have, right? 4 kind of percentage that we have. This is your weight by weight percentage, weight by volume percentage, right? Then you have volume by weight percentage, then volume by volume percentage, right? Remember one thing, always weight will be in grams here, volume will be in milliliters here. Now, if you have to write the formula of weight by weight percentage, that will be weight of solute by weight of solution multiplied by 100. Weight by volume is weight of solute by volume of solution. Volume by weight is volume of solute by weight of solution. Volume by volume is volume of solute divided by volume of solution multiplied by 100. Okay, units I have told you, simple way to understand these formulas. Okay, now if they have asked you for parts per million, now when you had percentage means 100, that's why you multiply that by 100. But if they are asking you ppm, parts per million, for example, if solute is at a very low amount, for example, carbon dioxide is just 0.03 in our atmosphere, that is a very low amount, right? So that's why we will say to calculate the ppm of carbon dioxide, that will be number of parts of carbon dioxide divided by total number of parts of all, multiplied by 10 raised to power 6, because million means 10 raised to power 6. Percentage means 100, that's why we multiply that with 100. Here we will multiply this by 10 raised to power 6, right? Okay, next is relation between molarity and molality. Molarity and molality. So it's a very simple relation. If they ask you molarity and they have given molality, they have given density, they have given molar mass of solute. So I'll just represent what are these symbols. M is equals to molality. M is molality. Capital M is molarity. Molarity. M2 is molar mass of solute. Molar mass of solute. And D is the density. D is the density. Okay, so everything they can give you, like from these 4 things they can give you 3 and they will ask you the last one, right? They can ask you molarity or density, right? Anything they can ask you, you just need to apply this formula, put the values and you will get your answer, right? Okay, now very important thing of this chapter, right? That is solubility. Now, what exactly is solubility, right? Solubility is when something is being dissolved in an amount of solvent, right? So it is maximum amount of solute that can be dissolved in a specified amount of solvent at a given temperature, right? So when you are dissolving sugar into the water, you are mixing it, say 1 spoon can be easily mixed, 2 spoon can be easily mixed. Maybe at 3rd or 4th spoon, you will say, okay, I'm not able to mix the more sugar into the water, right? So that means it has achieved the solubility. No more amount of solute can be dissolved in that amount of solvent. So because of this, it depends on nature of solute, solvent, temperature and pressure, right? All the things should be constant. Now solution based on the solubility are of 2 types. Saturated is that one when no more amount can be added into it. It is a solution in which no more solute can be dissolved at the same temperature and pressure. You are not able to add the 4th spoon of sugar into the water. That means that is the maximum that water can dissolve, right? So no more amount will be dissolved. Unsaturated solution is that if intentionally you will increase the temperature, like you will do something so that more solution can dissolve more sugar into it, right? So it is one in which more solute can be dissolved at the same temperature, right? At the same temperature. If like you're increasing the temperature, that's a different thing that I'll tell you. But if keeping the temperature constant, like I have to dissolve this more sugar, then that becomes a unsaturated solution, because it is saying that okay, I can't dissolve more sugar. You are like forcefully dissolving more sugar into it, so that will become the unsaturated solution. Okay, yes. Now let us see very important thing, the equilibrium between dissolution and crystallization. So I will show you this with the help of a diagram, right? So let us see, this is your beaker, right? You had water molecules. I am drawing this by blue, right? So you had water molecules all over the beaker. Okay, all over the beaker you had water molecules, blue color. Now, sugar, I am writing this by white. So you dissolving one sugar, sugar is being dissolved here. Now, it has reached its saturation point. Now, the extra amount of sugar that I am dissolving, I am showing this by this pink pen, right? I am adding this one more sugar. Now, this pink is telling me that this sugar is not getting dissolved in the solution. Now, what will happen? What we will think that this pink sugar is not getting dissolved in the solution. But actually what is happening? In reality, this pink part is getting dissolved. For example, let us say this is the pink solution, right? Now, this pink part is actually getting dissolved. If I talk about this one, okay, let's just how to erase this. Wait a minute. Okay, I'll just use this one, right? So, suppose this pink part is getting dissolved here. What just happened? I think I should not have done that. No worries, I'll do that again, right? Okay, I think it was somewhere here. Okay, I'll just draw the beaker again, right? They're just trying to do something new, but that definitely got failed. So this is the beaker, right? I'm drawing the water molecules here, right? And this I'm adding the sugar particle. Now, if I dissolve more sugar particle, now it has reached the saturation point that I don't want to dissolve more sugar into it. Now I'm forcefully adding one more sugar particle here. Now what will happen, guys? Very important thing. We will feel that the sugar is not being dissolved. But in reality, the sugar is getting, this extra sugar is getting dissolved here. This extra sugar is getting dissolved here in the solution. It is getting dissolved here in the solution. But one sugar which was already dissolved in the solution, that got crystallized here. If again I am adding one more extra sugar, again this extra sugar will get dissolved in the solution, and one more already dissolved sugar will get crystallized here. Right? Got it? So this is basically the equilibrium between dissolution. That means this extra sugar is getting dissolved, but what it has to sacrifice, that the already dissolved sugar will get crystallized out as sugar molecule. Right? So that is why we have written it here, that on dissolving the solid sugar in a solvent, its concentration increases. This is called a dissolution. While when some soluble particles in solution collide with the other solute particles and get separated out of the solution, this process is called crystallization. Right? So they were telling you about the dissolution crystallization, when sugar, already dissolved sugar, crystallizes out as sugar particle, right? That is called crystallization. Now they are saying this dynamic equilibrium that I explained you here, it is the condition where number of solute particles going into the solution is equal to the solute particle separating out. This is what I was showing you, that one sugar, if I am saying that one sugar I am dissolving here, now this sugar is already undissolved. Now if I intentionally dissolve the sugar, right, then one already dissolved sugar will get undissolved, right? This is the dynamic equilibrium that they are talking about, right? Dissolution and crystallization occur at the same rate. They are in a dynamic equilibrium. Okay. Now, from Lee-Chartlier principle, what we can say, this is actually the dependence of solubility, right? In case of solids and liquids, gases and liquids, right? So I have just written out the conclusion part of this, from where the question has been asked in your KCET. From this part, the question has been asked directly. I'll show you the question as well in today's lecture itself, right? So this is your NCERT statement, and this is a simple explanation of that, right? So basically, whenever you have solids in liquids, you are dissolving solid in the liquid. In that case, if you increase the temperature, how it will affect the solubility? If it is an exothermic reaction, that will decrease. If it is an endothermic reaction, that will increase. This is according to the Lee-Chartlier principle that says if in a nearly saturated solution, the dissolution process is endothermic, that means delta H is positive. Now we have a equation in chemical equilibrium, if you remember that, their delta H and temperature dependence formula we have. Now depending upon delta H is positive or negative, temperature variation happens, right? And depending upon that, the solubility, the equilibrium constant will increase or decrease. Now we are taking S as the equilibrium constant here, right? So as increasing the temperature in an exothermic reaction, solubility will decrease, as they have stated here. For exothermic, delta H is negative, so solubility will decrease. For endothermic, delta H is positive, solubility will increase, right? And there is no effect on the pressure. Why? Because solids are incompressible in nature. We can't compress them. That's why there is no there is no effect of increasing or decreasing the pressure here, right? Okay. Now gases and liquids. Okay. Now this is very interesting. Gases and liquids. Just imagine that you are drinking a Coke bottle, right? Now you know that there we have carbon dioxide is dissolved in it. Now, as we increase the pressure, increase the temperature, solubility will decrease. Now, how can we say that? How can we say that solubility will decrease? Right? Now, as we increase the temperature, what will happen here? The particles of the gases, they will get kinetic energy. They will move here and there, move here and there, here and there. And what will happen? The solubility, the dissolution process will decrease. Right? Now, pressure. If you increase the pressure, if you increase the pressure, sometimes I get too excited while teaching, right? So if you increase the pressure, right, you are applying the pressure. We know that the molecules are getting closer to each other. If I increase the pressure, molecules are getting closer to each other, then definitely solubility will increase, because dissolution is increasing in this case, right? Whenever dissolution is increasing, solubility is increasing. Now sugar, ma'am, dissolved in water. Ma'am, is this an endothermic or exothermic reaction? See, sugar dissolved in water is an endothermic reaction, right? You need to give it energy. When you're dissolving sugar, it will not give you energy. You will not see that sugar is getting dissolved in the water and you see some kind of heat is produced in the water. No, nothing like that happens, right? So you have to mix it. That means you are giving it mechanical energy, right? So that is why energy is required. That's why it is endothermic in nature. That is why when we increase the temperature, solubility will increase, and that is why in whenever we are making gulab jamun or any good sweet where we need very viscous sugary water, what we do, we add the sugar, we increase the temperature, right? Even while making some good chutneys, right, what they do in the kitchen, they just put sugar into it and heat it so that a very viscous amount of sugary solution we can get out of that, because on increasing the temperature on endothermic reaction, solubility increases. Okay, understood? Now next is Henry's law. Now Henry's law. Now what is Henry's law? Again, the question has been asked in previous 2 to 3 years regularly on the Henry's law. Okay, so what is exactly Henry's law? Henry's law tells us that how on increasing the pressure, solubility increases when in gas and liquids, when we dissolve gas in the liquids. Basically, he is telling us about this thing. When you increase the pressure, solubility will increase. Okay. Achha, before that, I forgot to tell you one thing. Fishes in cold water. This is very important concept. From here also the question can be asked. Right. Now, this is fishes in water. Now, when you increase the temperature, solubility decreases. This I told you. Now, fishes, aquatic life, when they want to survive in water, right, they want oxygen, right, they want oxygen. That is why whenever the temperature is high, that is why what you will observe always, that when in the cold temperature, right, when the temperature is less, solubility is high. That is why fishes find it very easy. You will see fishes, right, they are surviving, able to survive in cold water. But if there is too much heat, too much sun, what will happen? You will see fishes on the surface. Why? Because it is very difficult for them to breathe in the water. Because when sun is falling on the water, the heat energy of sun will increase the temperature of the water. When the temperature of the water will increase, the solubility of oxygen dissolved in the water will decrease. Aquatic life will find it very difficult to breathe. That's why in summers you will find that fishes, aquatic life, they will be on the surface of the water because they want to inhale, they want to survive. Right? Now, talking about pressure and solubility, we will see this in this page, right, by Henry's law. Okay. Now, at constant temperature, that means definitely it is dependent on the temperature. The solubility of a gas is directly proportional to the partial pressure of the gas. The partial pressure of the gas, right, above the surface of liquid or the solution, right. Now, that means solubility is directly proportional to the pressure, right. So, reversing this, we can say pressure is directly proportional to the solubility, right. Now, we just need to put a constant here, and by eliminating this proportionality sign, we have equals to this proportionality constant, that is Henry's constant. Now, this is not your full-fledged answer. This is not your full-fledged answer. After this, Dalton will say that, okay, why don't we write solubility in the form of mole fractions, right? Unit of solubility is same as the concentration. Now, if you want to write, if you write the solubility in mole fraction, then it will become as this. This is the mole fraction. So now this is your main formula, that partial pressure of a gas is equals to Henry's constant multiplied by the mole fraction. And if you compare this and draw a graph from here, y is equals to mx plus c. This is your straight line graph, right? If you draw a straight line graph from here, what you will observe? What you will observe, guys, from here? This is y, this is y, this is y-axis definitely p. Slope is definitely, if this x is your mole fraction, then slope is definitely kh, which is a positive slope. That means it will be upwards, and intercept is 0. That means this will go from 0 to this point, right? This is your slope, this is your graph, and here slope is kh. This is your graph of partial pressure versus mole fraction, right? Okay, now next is higher the value. Now we are talking about the dependence here. Higher the value of kh at a given pressure, the lower is the solubility of the gas in the liquid. So we are talking about the kh at a given pressure. If pressure is constant, this is P is equals to kh psi. P is constant, this will be a constant thing. That means these two will be inversely proportional to each other. That means if pressure is constant, then chi, mole fraction, and kh are inversely to each other. So here we can say higher the value of kh, lower is the solubility of the gas. That means lower is the mole fraction, because you can write it here, because at a constant pressure KH is inversely proportional to mole fraction. That means inversely proportional to solubility. Right? Okay. Understood. Solubility of the gas increases with increase in pressure. This we have already seen. Next is application of Henry's law. Very, very important. We have three applications of Henry's law. Third, I will write it myself here. Right, everything I have written myself only, but I will write in front of you only. Now, Henry's application are three application basically. First is your soft drinks. Right, we know that why we want to drink cold soft drinks. Why do we want to heat up the soft drinks and then eat it? Then drink it. Why? What is the reason? The reason is at low temperature there is high solubility. Right? At low temperature there is high solubility. At high pressure there is high solubility. That is the reason we keep the cold drinks at a very low pressure, at a very low temperature and at a high pressure. Right? That is why when you open a Coke bottle, right, you will see a brisk thing that is coming out of it. That is basically carbon dioxide. Right? So when you increase the pressure, carbon dioxide will come out of that. Solubility of CO2 in soft drinks and soda water. The bottle is sealed under very high pressure. Next is scuba divers. Now these scuba divers, we know that when we are going in the ocean, right? So in the ocean the pressure is high. Right, that is why the solubility will be high. That is why in our bloodstream, whenever we are inhaling a gas, right, so that gas will be easily dissolved in our body. Right, that is the reason, because of high pressure the solubility in the bloodstream is also high. That is because of this high solubility everything is fine till then. When you are under the water everything is fine, but when you come out of the water, right, after the diving we come out of the water, what happens? Now solubility was very high, right, the blood was getting that high solubility gases inside it, but now the solubility suddenly drops. Why? Because the pressure is decreasing as we are coming out of the water. Because the pressure is decreasing, the solubility is also decreasing. Now because the solubility is decreasing is the reason your blood will, your basically your internal system, your veins, they can have a condition like bends because of this fluctuating solubility of the oxygen inside the blood. Right, that means first it is highly soluble, then solubility decreases. Because of that reason there is condition which is very, very disastrous, that is bends. Now to avoid this bend situation we need an inert gas. Now this inert gas like helium is added into our scuba divers that thing in that chamber in which they have filled the gas. Right, in that helium gas is filled because it is inert. Even if it comes inside the body it will not react with our body. It is also not harmful for us. Right, so now to avoid bends and toxic effect of high concentration of N2. Right, N2, because in our atmosphere there is N2, that's why in that also we add N2. Right, in the blood the cylinder used by scuba divers are filled with air diluted with helium gas. Right, okay. Third is anoxia. Anoxia means a condition of unconsciousness, falling down, right, even leading to death. Right, so it is suffocating condition. Basically what will happen here, when we are moving up, when we are going into the higher mountains, right, now what will happen? Pressure will decrease. Right, pressure will decrease. Because the pressure is decreasing, that is the reason solubility will decrease. Because the solubility is decreasing, the people who are not very habitual of living in suffocating areas, right, they will find it very difficult. That is why to higher mountain it can even lead to death, and I think you must have heard a lot of incidents related to this. Right, okay. Next is Raoult's law. Okay, now I'll just drink water and we are going to start Raoult's law here. Okay. Now, what is Raoult's law? If you talk about Raoult's law, Basically it is a base of ideal non-ideal solutions, right? Solubility is a concept from where theoretical questions are asked, right? From Henry's law, numerical based question can be asked, even theoretical. From here mostly the numerical questions will be asked, right? So basically here firstly we need to do what is the difference between vapor pressure and partial vapor pressure. So I'm drawing this line here, right? So if you talk about, there is a beaker here and this is another beaker. Here you have solution 1. Here you have solution 1. This is solution 2. And when you mix it, you will have the third solution. That is the solution 1 plus 2. That is solution 1 plus 2. Okay. In solution 1, I am denoting it by blue dots. Okay. The molecules are these. These are the molecules of solution 1. With pink dots, these are the solution, these are the particles of solution 2. Okay, these are the particles of solution 2. These are the particles of solution 2. Okay, now next thing is, when we mix them together, what we will have? When we mix them together, what we will have? We will mix them together and what we will have? Can you see this? Can you see this? Right? Now this is very simple. Now from here I will teach you what is the difference between vapor pressure and partial pressure. Now this is first component. If it is individually present, for example, you are studying individually in your room. There is no one in the room, you are self-study you are doing. Right? So this is your vapor pressure. This is vapor pressure. This will be denoted by P01. When you are individually studying, when 2 number is individually there in the solution, there is no other component, that is called vapor pressure of the second component. Now, when you mix them together, you will have P01 and P02, both of them. But now the thing is that this P01, P02 is not alone. Now when you are studying alone, you have a different concentration, different focus. When you and your friend are studying together in a room, you guys will talk also, you guys will gossip also, you guys will discuss also. That is why that is going to affect the focus and concentration. Maybe it will benefit you, maybe it will not benefit you. Right? So that is called partial pressure. Partial means parts. Now the full concentration is not yours. You're also talking, gossiping, thinking this and that. Right? So here it is called as P1, that is, and P2. This is called the partial pressure. So you can write it here. This is the vapor pressure of pure component, right? And this is these are the partial pressures. These are the partial pressures of the component in a mixture, right? So now Raoult's law has given us the relation between vapor pressure and partial pressure. He is saying that when you are sitting alone and when you are sitting with your friend, when you are sitting alone, you have P1 naught, and when you are sitting with your friend, you have P1. Right? Now, if you want to find out the relation between that is given by Raoult's law, that P1, that is partial pressure, is equals to vapor pressure of that component multiplied by the mole fraction of that component in the liquid phase. Right? This mole fraction is in the liquid phase, not in the vapor phase. Right? So P2 is equals to P2 naught multiplied by psi naught, that is the mole fraction of the liquid in the mole fraction of the second component in the liquid phase. Right? Okay, so now guys, we know that what is P total. P total means when you guys are sitting together, you guys are studying, what is the total study that you will do. That is 1 and 2, add both of this, you will get total. So it will be P1 plus P2, right? What is P1? P1 is nothing but it is P1 naught psi 1 plus P2 naught psi 2, right? Now we know that psi 1 plus psi 2 is equals to, chi 1 plus chi 2 is equals to 1. So chi is what? Now if you want to substitute anything, you can substitute anything. I want to substitute the value of 2 here. So it will be P1 naught chi1 plus P2 naught 1 minus chi1, right? This will be equals to P1 naught chi1 plus P2 naught chi1. Wait a minute, this will be P2 naught minus P2 naught chi1. Right, you can just take chi1 as common, that will be P1 naught plus wait a minute, this will be minus P2 naught plus P2 naught. So that will become your answer in the form of chi1. If you want to have the answer in form of chi2, you can substitute chi1 is equals to chi2 minus 1 minus chi2 and you will get the answer in the form of chi2. Okay. Now, this is your Raoult's law. Now, second is, as I was stressing upon one thing, that if you have chi1, that is a vapor pressure, or you can say that is a mole fraction in the liquid state, not in the vapor state. But this Y is the mole fraction. They have written it here only, right? I have written it here only. Mole fraction in the vapor phase, right? Y is the mole fraction in the vapor phase. Right, so as guys you can see here, P1 P2 is equals to P1 is equals to Y1 into PT. PT is the total pressure and P2 is equals to Y2 into PT. And from this question, from this and this together, they have asked you a question in your KCET previous year questions. I'll show you that question in the end of this lecture. In the end of this lecture, I'm going to show you that question also, right? So that you're able to understand that how these things are very, very important for you. So this becomes also very, very important for you. Now, talking about the ideal and non-ideal gases, right? So that is basically based on Raoult's law. So now, like we talked about ideal gases, right? The one which obey ideal gas law, PV is equals to nRT, is ideal gas, non-ideal gas. Similarly, we have ideal solutions, non-ideal solutions, and that is based on the Raoult's law. Ideal solution is one which is obeying Raoult's law. Non-ideal solution is the one which is not obeying Raoult's law. Okay, so ideal solution obey Raoult's law over entire range of concentrations, whatever is the concentration. In this case, delta H mixing, that means the enthalpy in the mixture is 0, right? That means the delta, the change in enthalpy is 0. Change in volume is also 0, right? Now, why it is so? Because AB, we are saying that because AB interactions are same as AA and BB interactions. There is no difference in that. If you feel that, for example, N-hexane and N-heptane. N-hexane and N-hexane has same interaction as N-pentane and N-pentane, and N-hexane and N-heptane also has same interaction. That means AB interactions is equals to AA is equals to BB interactions. Other example is benzene and toluene. Other example is benzene and toluene is one more example for that. Right, now as you can see the graph here, everybody, as you can see the graph here, so this is the vapor pressure, this is the mole fraction, right? So this is the vapor pressure, this is the mole fraction. As you can see here, when moles of 1 is 0 but the mole fraction of 2 is unity, in that case it will start from 0 and will come to this point. This is partial pressure of second component. This is partial pressure of first component when mole fraction of first is unity, right? And this is total pressure, that will be equals to P1 plus P2. That is equals to P1 plus P2. This is for ideal situations, ideal solutions like these, right? But if you talk about non-ideal solutions, non-ideal solutions are the one which do not obey, which does not obey Raoult's law, right? So basically they don't obey this law, that do not obey Raoult's law over entire range of concentration. Here we can say that PT is not equals to P1 plus P2, right? That is not equals to P1 plus P2. Right, now here delta H mixing is also not 0, delta V mixing is also not 0. Moreover, the interactions of AB are not equals to AA or BB interactions. Right, we will see this through the examples. Right, now in non-ideal solutions, right, it doesn't matter whether it's positive deviation or negative. Basically, non-ideal solution are of two types, positive and negative deviation. It doesn't matter whether it is positively deviated or negatively deviated. You will always see that delta S mixing is always greater than 0. That means entropy is always increasing, and delta G is always decreasing. That is, it is always negative. It doesn't matter whether it's a positive deviation or it's a negative deviation, right? Next is this thing, very important, very important. As you can see here, positive and negative deviation. From here also the question can be asked, right? Can you see this here, positive and negative deviation? Positive deviation is when your, see you, how you can understand this, just remember a story here, right? So you and your friend were studying together, right? Positive deviation means you guys are studying more. Now tell me, you and your friend are sitting together when you guys are studying more, when the interaction is less, when you guys are not talking to each other. So if the interaction is less, then there will be positive deviation. That means you both are focusing on the study. If you guys are more attracted toward each other, there is more interactions, you're gossiping about this and that, then there will be negative deviation. That means you are not focusing on the study. This is the best way to remember this. Right, now AB interactions are less than AA and BB interactions. Here AB interactions are more than AA or BB interactions. Right, I'll show you how we can tell about the interactions here. As you can see the examples here. Now I'll give you more examples, but for those examples you need to visit my Telegram channel, that is Diksha Kaushal Chemistry Official. Right, now in that channel you will get my photo of this, but I'll write all the examples there that can be asked to you in the exam. Apart from that, nothing they can ask. I can guarantee you that. Right, so for that you need to visit the Telegram channel of V Karnataka, KCET and boards and Diksha Kaushal Chemistry Official. Right, now that is positive deviation. Now let us see, positive deviation means interactions are less. Now see guys, very simple thing how you need to use your brain. We know that ethanol has hydrogen bonding. Right? Ethanol, OH will have hydrogen bonding. Now when you add acetone means CH3, C double bond O, CH3. Now ethanol and ethanol will have a stronger hydrogen bonding, but when you add acetone into it, the hydrogen bonding of this ethanol molecule will decrease. That is why the AB interactions are weaker as compared to AA interactions. Hence we can say this is positive deviation. If you talk about carbon disulfide and acetone. Now carbon disulfide is a non-polar molecule. It is a non-polar molecule, and this acetone is same as CH3, C double bond O, CH3. Now acetone will have, because of this oxygen is like highly electronegative, because of this it will have strong van der Waals interactions, dipole interactions. But when you are adding a non-polar molecule, the dipole interactions will decrease, and hence the interactions will decrease here. Right, then you have negative deviation, that means interactions are more. In this case what you will observe that phenol, which is definitely having hydrogen bonding before, phenol is what this, phenol is having this kind of thing. Right, what is aniline? Aniline is this kind of thing, right, this kind of thing. Now if you talk about phenol and aniline, what you will observe, we know that oxygen is more electronegative as compared to nitrogen. So the hydrogen bonding of hydrogen and oxygen is more. Hydrogen bonding of oxygen and hydrogen is more as compared to nitrogen and hydrogen. As compared to nitrogen and hydrogen. Now what you will observe here, very important thing, the hydrogen bonding is less, but the number of hydrogen bonds will be more. Now it has only one hydrogen. for the hydrogen bonding. When you add aniline into it, it has 2 hydrogens. So what will happen? With this oxygen, now you have 2 more hydrogens to form the hydrogen bonding. That is why this hydrogen can form hydrogen bonding with this one. This can form hydrogen bonding with this one. This can also form hydrogen bonding with one more oxygen molecule, and this is how the hydrogen bonding is going to increase in this case, right? Next is chloroform. Next is example is chloroform and acetone. See, chloroform is basically CHCl3 and acetone is CH3 C double bond O CH3. Now guys, when in acetone you are adding a compound that is non-polar, it will decrease the interactions. But if you are adding a polar molecule here, this is a polar molecule. When you are adding a polar molecule, it will increase the interactions. There will be more interactions. More interactions means this is negative deviation, right? Okay. Now let us see what are the important points here. First is delta H mixing is greater than 0. Delta V mixing is also greater than 0. Delta S and delta G will be same. Now, when you draw the graph, it will be above. It will be above. It will be above. Right? Now, if you talk about this one, delta H mixing is less than 0. Delta V mixing is less than 0. And this will be below. This will be below. This will be below. Right? This is going to be below here. Right? Okay. Okay, everybody. Now, let us talk about azeotropes. Let us talk about the azeotropes. They are somewhat similar to negative and positive deviation only, right? So, we will see that. See, if you talk about azeotropes, what is the definition? The binary solution having solute and solvent that have the same composition in liquid and vapor phase and boils at a constant temperature, right? They have the same composition, liquid and vapor phase, and they boil at the same temperature are called azeotropes. So what you need to understand here, there are 2 types of azeotropes, maximum boiling azeotrope and minimum boiling azeotrope. If you talk about maximum boiling azeotrope, they are basically the ones which are showing negative deviation. Can you tell me why? Can you tell me why? Can you tell me why? I'll tell you why. See, in negative deviation, total pressure is less than P1 plus P2. Here, total pressure is more than P1 plus P2. Tell me what is a boiling point. A boiling point means, the definition, this we will do in the elevation of boiling point as well. Right, a boiling point means the temperature, right, at which the vapor pressure, for example, this is the vapor pressure. We are increasing the temperature, vapor pressure will increase. On increasing the temperature, at that temperature where vapor pressure is equals to atmospheric, this is atmospheric pressure, that is called as boiling point, right? That is called as boiling point. Now, okay ma'am, we need to equate vapor pressure with the atmospheric pressure, we got it. But ma'am, what is the link with this thing? We know that the pressure is increasing in this case. If this was the pressure earlier, now this is the pressure. That means the boiling point that you require is less. See guys, understand one thing, that earlier, if I say earlier the total pressure was this. But now the total pressure, this is your atmospheric pressure, this is your vapor pressure, so this is your total pressure. Earlier it was this, but now this is equals to this. Now that means earlier we required, wait a minute, yes, this was the vapor pressure before, this is a new vapor pressure, right, on adding the solute and solvent interactions. What you observed, the boiling point has decreased. Earlier it needed this much boiling point. Now it needs this much boiling point. That means decrease means minimum. That is why in the minimum, this will be minimum. In the minimum boiling point you have positive deviation. because in the positive deviation boiling point has decreased. Okay, so but if we talk about the negative deviation, if you talk about the negative deviation, this was your atmospheric pressure, this was your atmospheric pressure, right? I am saying that this is your initial PT, but with the negative deviation, partial pressure, total pressure has decreased, right? That means this is your final. Now, earlier you needed this much amount of temperature, right? That means, but now you need this much amount of temperature. Now you need this much. Here temperature has decreased, here it has increased. That means it is maximum boiling azeotrope. This is a way to remember this thing, okay? Right? That's why for maximum boiling azeotrope we have negative deviation. For minimum we have positive deviation. Right? Okay. Now the examples will be same. The same examples that you have done for negative deviation will be applied for maximum boiling point, because nitric acid and water, the interactions are increasing here, right? How the interactions are increasing here? Nitric acid, HNO3, right, and water, this is water, right? So what will happen here? The hydrogen bonding is going to increase in this case because of 3 oxygens here, right? And in this case what you will see, ethanol already had hydrogen bonds, right? Both had hydrogen bonds, but you know ethanol has weak hydrogen bonds as compared to water, strong hydrogen bonds. So when you are adding ethanol into the water, the strong hydrogen bonds are converted into weak hydrogen bonds. That means interactions are decreasing here, right? Okay. Now next is colligative properties, a very important topic. Surely you are going to see questions on this. Now let us start with the colligative properties here. As you can see, colligative properties, guys. Colligative properties are the properties of solution which depends only on the number of solute particles, right, irrespective of their nature relative to the total number of particles present in the solution. It doesn't matter. They will directly depend on the number of solute particles. Colligative property directly proportional to number of particles in the solution, right? The inversely in the solution means number of solute particles, okay? Right, you just need to write here number of solute particles, okay? Just write here, wait a second. Okay, so we'll just write here number of solute particles. Okay, so you can also write it like this, okay? Number of solute particles in the solution, okay? Number of solute particles in the solution. We know that number of particles, that is number of moles, is equals to weight divided by molar mass. That is why colligative properties are inversely proportional to the molar mass, right? Okay. Now we have 4 colligative properties. First is relative lowering in vapor pressure, elevation in boiling point, depression in freezing point, and osmotic pressure. All these 4 things we are going to do in detail, right? Now first is relative lowering in the vapor pressure. If you talk about relative lowering in vapor pressure, see, very simple way I will teach you this, right? So we know that whenever we are adding non-volatile solute, so just imagine this is a beaker, okay? I'll just draw it here only, right? So this is the beaker, this is the beaker. Now you have solvent particles here. You have solvent particles here, right? Now you will be adding in all the cases we are adding non-volatile solute. That means which is not converted into vapors. So whenever we are adding non-volatile solute, just imagine all of them can be converted into vapors, right? We are adding non-volatile solute which cannot be converted into vapors. That means definitely earlier the vapor pressure must be due to all the particles here which can be converted into vapors. But when you are adding that particle which cannot be converted into vapors, now this will reduce the overall vapor pressure because these particles cannot be converted into the vapor phase. So vapor pressure is going to get decreased. It's the same as you want to meet your favorite celebrity, right? You will go there. For example, there are bodyguards, right, which will not let you meet your favorite celebrity. So now what will happen, right? That means that person will not be able to get out of get out of their house and you can see them. It's not possible. Reason is because security is very high. So these number of solute particles are like that security only, right? Okay, so number of solute particles if non-volatile are added, so vapor pressure is going to decrease here. That is the reason when number of solute particles increases, vapor pressure will decrease, right? Non-volatile solute is added to the solvent, the pure vapor pressure of solution becomes lower than that of pure solvent. For pure solvent, P1 naught is vapor pressure of pure solvent, right? Okay, what about P1? P1 is partial pressure of solution, of solvent in solution. For solvent, that's why we have written 1, 1, 1. Okay, this is vapor pressure of pure solvent. This is partial pressure of solvent in the solution, right? So here what we will see, this delta P1, we know that, see, very simple, because we know that P1 naught is greater than P1. Reason being because vapor pressure has decreased, right? So that's why delta V, if they ask you simple lowering of vapor pressure, this is called lowering of vapor pressure. This is called lowering of vapor pressure. If you want to see the relative lowering, you need to divide it by the P1. That will be relative lowering of the vapor pressure, right? So that is relative lowering of the vapor pressure. This will be divided by the original. That means P1 naught will be there, right? P1 naught will be there. And here you see your full answer, right? You see your full answer. Now they are saying that relative lowering of vapor pressure, it is a colligative property because it is directly proportional to the number or to the mole fraction. Mole fraction means number of solute, mole fraction of 2. Mole fraction of 2 means this is of solute, mole fraction of solute, right? So now this means N2 by N1 plus N2. We know that N1 is very small, or you can say N2 is very small, not N1, because N1 is solvent, so solute is always smaller than solvent, right? So N2 is small as compared to N1. So here we can directly write it as P1 naught minus P1 divided by P1 naught will be equals to N2 by N1, right? Because N2 is very small. What is number of moles of 2? That is weight of 2 by molar mass of 2. Right? What is N1? Weight of 1 solvent divided by molar mass of 1. And this will become your full-fledged answer. Right? This will become your full-fledged answer. From here you can solve all the numericals based on relative lowering in vapor pressure. Just remember, this is called the relative lowering. This is called the relative, or you can just directly write RLVP. Okay, relative lowering in vapor pressure. But if they ask you lowering in vapor pressure, just see the question, okay? Lowering in vapor pressure. If they ask you lowering in vapor pressure, that is equals to P1 naught minus P1. P1 naught minus P1. Right? Okay, P1 naught minus P1. Understood? Easy. Now, next is elevation in boiling point. What about elevation in boiling point, everybody? Second case is elevation in boiling point. Now, it's also very simple to understand. I'll just give you a simple way, right? I told you that what is a boiling point? A boiling point is that temperature where the vapor pressure is equal to atmospheric pressure. If this is atmospheric pressure, this is the vapor pressure. Once this become equal, this will be the boiling point, right? We know that vapor pressure is decreasing. Let's assume this is your atmospheric pressure. This is atmospheric pressure, right? And I am assuming that earlier this was the vapor pressure of pure solvent. This is the vapor pressure of pure solvent when you have not added solute. Now we know that when we add the solute, the vapor pressure of solvent will decrease. This so we have seen it here only. The vapor pressure of solvent will decrease, right? That will decrease. That means the vapor pressure of the solvent will be this one. It will decrease further. This is the vapor pressure of the solvent in solution. In solution, right? It will decrease. Earlier, what amount you needed? This is the initial amount when there was only the solvent. This is represented by TB, boiling point of pure solvent. That is why there is one knot there. What is the boiling point of solvent in the solution? That is TB. We know that boiling point has increased. That's why it is called elevation in boiling point. TB is greater than TB naught and delta TB is equals to larger minus smaller value, that is TB minus TB naught. Okay, understood? A simple way to understand this thing here, right? The boiling point of a liquid is that temperature which its vapor pressure becomes equal to the atmospheric pressure. Okay, to the atmospheric pressure. Now this is your graph. This is the graph as you can see here. This is the vapor pressure. This is the temperature. We are saying that this is the atmospheric pressure where it need to become equal. Right? This is a graph. This is the point of pure solvent. Right? Pure solvent, it is increasing and it is touching the atmospheric pressure at this point. This is the point which is called the TB naught, where vapor pressure of solvent is touching the atmospheric pressure. Now we know that vapor pressure will decrease in a solution. So once it has decreased, now it is touching the atmospheric pressure at a larger temperature, that is TB, and this difference is called the delta TB. Right? This is from the graph also I have shown you. Right? Okay. Now let us see the mathematical terms about it. Delta TB is TB minus TB naught, right? TB, delta TB is directly proportional to molality is equals to Kb into molality, right? What is this Kb? Kb is the alebuscopic constant, right? Or you can also say this is molar elevation constant, right? And one more thing to remember here, the units are Kelvin kilogram. This is Kelvin kilogram per mole. These are the units. Okay, now this is the formula. This is not required, but you can just go through this formula. Hardly they will ask you this, but my duty is to tell you that this is mentioned in your NCERT. Right? Now here the formula will become delta TB is equals to Kb. Can you tell me what is the formula of molality? Molality is equals to number of moles of solute divided by weight of solvent in kilogram. In gram it will be multiplied by 1000. Now can you tell me what is this value of N2? N2 is nothing, it is W2 divided by M2. Right? This becomes your full-fledged formula. From here also the question has been asked in your KCET last 2 to 3 years paper. Right? Okay, that's why this becomes very, very important for you. Right? Next is depression in freezing point. Now let us talk about the depression in freezing point. Now you need to answer me firstly, what exactly is a freezing point? Right? What do you mean by a freezing point? A freezing point is that situation in which the vapor pressure in the liquid phase become equals to the vapor pressure in the solid phase. Right? So, freezing point is the temperature at which vapor pressure of the substance in its liquid phase is equals to vapor pressure in the solid phase. That is the definition. Now, how we will answer this from the definition? I am saying that this is your, just imagine this is your this is your vapor pressure in solid phase. This is the cutoff that you need to achieve, right? Now, this one is vapor pressure of pure solvent, right? We know that. And we know that the vapor pressure will decrease. That's why vapor pressure of solvent in solution will become this. Right? Now students, tell me one thing. The vapor pressure in the solid state will be more or less? The vapor pressure, see, tell me one thing. Solid has less vapor or more vapor? Solid, the molecules are very near to each other, so it will form less vapor. So that is why vapor pressure of solid is always less than vapor pressure of liquid. Do you agree with that? Right? So instead of writing it here, I will write it here, isn't it? Because vapor pressure of solid is definitely less than the vapor pressure of solvent in liquid phase, right? So I'll just write it again. I'll just draw it this again. If you draw this here, this is vapor pressure of solvent in solid phase, right? This is vapor pressure of solvent, pure solvent in liquid phase. This is vapor pressure of pure solvent in liquid phase. Vapor pressure of pure solvent in liquid phase only, but in liquid phase in solution. Now we have also added the non-volatile solute here. This was pure, this was pure. This was in solid, this was in liquid. That is why solid is less than the liquid, right? Now we have added solution, so vapor pressure has decreased here, right? Earlier, this is our cutoff that we want to achieve. Earlier, this was the temperature that was required, that is freezing point. Now this is for pure solvent. This is pure solvent. This is pure solvent. Right? This is pure solid. This is pure solid. And this is the solution. Right? So this is the temperature that was required. That is TF naught. Now this is the temperature that is required. Right? Because it is in the solution phase. So it is called TF. As you can see, TF naught is greater than TF. That means the freezing point. That means, can we say that the freezing point has increased or decreased? Wait a minute. The freezing point, earlier it was vapor pressure of the pure solvent. Depression in freezing point, no? Depression, obviously, yes. So this is TF naught is greater than TF. Now after adding the solvent, after adding this non-volatile solute into the solvent, the freezing point has decreased. That is called depression in freezing point, right? And this thing is also used in your daily life. You do one thing, you take a glass of water, right? You just drink it as it is. You just, take 2 glasses of the same volume, right? So now in one glass you add salt into it, in another glass don't add salt into it, right? So you will see that the one which has salt will not be freezed at that temperature. But for example, you kept it for 3 hours. After 3 hours, what you will see that the one which don't have salt will be totally freezed, but the one which has salt will have the lower freezing point. That means that will not be freezed as compared to the one which has no salt. So that means freezing point has decreased. This is also used in petrols. For example, some car is going on at heavy mountains where there is like too much snow, too much temperature is really low, so that we don't want petrol to freeze, right? Otherwise how our car will move, right? So that's why we add ethylene glycol solution into the petrol, so that this don't get freezed. Okay, next is one more is anti-freezing agent. Basically it is used as anti-freezing agent. Anti-freezing agents are added. Then we also have, for example, what you will see in very hilly areas, right, because there is snow frequently, that's why what they do in hilly areas, they spread salt, right, onto the floor so that it does not get freeze easily, right. Okay, that's why the water of the ocean will not get freeze very easily, right, as compared to the normal water in our daily life, because ocean water has salt in it. That's why even in higher mountains you will hardly see that they will get freeze. Once the ocean is getting freeze, that means the temperature is even lower as compared to the freezing point, even after adding the, not adding the naturally salt that God has added, right. Now if from the graph we need to understand, so this is your frozen solvent, that means in the solid state. This is the where we want to touch it. So this is a liquid solvent, this is the way, this is the liquid solvent, right. Wait a minute, I'll just draw it as it is. This is the frozen solvent. With pink I was drawing the liquid, no, with pink I was drawing the liquid solvent, right, without adding the non-volatile solute. But once I add the non-volatile solute, it will become like this, right. So now when this is touching, when this point, this liquid solvent is touching the frozen solvent, it is called TF naught, it is called TF naught. When solution is touching the frozen solvent, that is called TF, that is called TF. And as you can see, TF naught is greater than TF, that means there is depression in the freezing point, and this thing is called the delta TF, that means the change in the freezing point, right. Okay. Now let us see the formulas here. What are the formulas, everyone? What are the formulas? TF is less than TF naught, that we know. This is same as elevation in boiling point only. The difference is here, larger is this and smaller is this. In delta TB, larger was this TB and smaller was this TB naught, right. So that is the difference. Here delta TF is equals to KF. What is molarity? Molarity is number of moles of solute divided by weight of solvent. So we can write weight of solute by molar mass of solute divided by weight of solvent multiplied by 1000. If weight is in grams, then this will become your full-fledged answer. This will become your full-fledged answer, right. This will become your full-fledged answer. Okay. Okay, guys. Now, what is Kf? That is cryoscopic constant or molar depression constant, right? The formula is this, right? It includes delta H of fusion, right? Okay. Next is fourth colligative property is osmosis. From here, theoretical questions are frequently asked, okay? So, we will see this property. What exactly is osmotic pressure? So, once you put water, or you can just have a glass of, not glass, you have a bowl of water and add some almonds into it, add raisins into it, right? What you will see after one day, and when you soak it, what you will see, it will absorb the water and it will get little bit swelled up, right? So now what we'll see, this is exactly this is what we call osmosis. Osmosis is basically the process of flow of solvent molecules from lower concentration to higher concentration. 3-4 definitions I will write here. First definition is solvent from high concentration to low concentration, low concentration to high concentration. This is for solvent. If you talk about solute particles that are in less quantity, they will move from high concentration to low concentration, right? Okay, so it depends which is the definition they have given you, right? Okay, now if they ask you the concentration, if they ask you the solution, definitely solution which has, okay, solution I will tell you when we will do this thing, only then you will be able to understand, otherwise you will get confused here. Now basically this is the semi-permeable membrane, from where we know that, see, very important thing is solvent particles are small, solute particles are big. Solute particles are big or large. Okay, solute particles are large. Tell me, water particle is small, or particle of water is small, or the particle of salt or sugar is small? Obviously water is small, right? Okay, so that's why I'm saying that. First you need to remember this, that which particle is actually moving. In reality, the solvent particle is moving, right? So this is a semi-permeable membrane, and this semi-permeable membrane will only allow solvent particles to move, not the solute particles, right? So this is your solution which is having solute also. This is the solution which is a pure solution, a pure solvent. This is pure solvent, this is solution. So you can write here, this is pure solvent. This is a very, very important concept. This is pure solvent and this is solute plus solution. This is the solution. Okay. Now, because just remember one definition. In osmosis, solvent particle move from low concentration to high concentration. Solvent is more here or here. First you need to tell me that. Solvent is more in this case or this case. Solvent is more in this case or this case. Definitely in this case. So here you can write one more thing, that in the pure solvent, solvent concentration is high. Solvent concentration is high. Solute concentration is low because it is 0 only. Right? Solute concentration is low. In solution, definitely as compared to that, solvent concentration is low and solute concentration is high as compared to the pure solvent. We are doing this comparison here. Now I have told you two things here, that solvent particles with the blue color I have mentioned, they will move from low to high. Low concentration is this, that means solvent particles will move in this direction. But solute particles, they will move in this direction. In reality, only solvent particle moves, but they can ask you that what is osmosis in terms of solute particles. So solute particles move from high concentration to low concentration. Right? Okay. Next is, ma'am, what you were talking about solution. Now tell me, if you talk about the solution, particles will move from solute to solution, solution to pure solvent, or pure solvent to solution. So you can write solvent particles move from pure solvent, no, not pure solvent, from solution to pure solvent, solution to pure solvent. Okay, understood this thing or not? Everybody, are you able to understand this thing or not? What is osmosis? Solvent from low to high concentration, right? And solute, this is the solvent particles, this is the motion of solvent particle, and this is the motion of solute particle. This is the motion of solute particles. Okay, right? Now, next thing is what is osmotic pressure? So when you apply external pressure here to stop this movement, right? When I apply external pressure here to stop the movement, if that external pressure is more than, if that external pressure is equals to the osmotic pressure, then I will say that that is called the osmotic pressure. Now, what we will do here, I'll just erase this thing. What is the osmotic pressure? Osmotic, the process of flow of solvent molecules from solution of lower concentration to higher. So this is called osmosis. What is osmotic pressure? That is a pressure that is present there in this movement. That is called osmotic pressure. Right? This is pi. This is represented by pi. Right? Pi is directly proportional to concentration. That means molarity. And here, if you just eliminate this proportionality sign, you will get RT here. What is C? C is basically the molarity. C is basically molarity, right? That's why we say that. That's why this is equals to number of moles of solute divided by volume of solution in liters. You need to write here liters. If you don't write here, if it is in milliliter, if this is in milliliter, then this will be multiplied by 1000. Then you have to write it here liters. Okay, write here liters. Okay, yes. Now it is used to determine molar mass of proteins, polymers and other macromolecules. To determine the molar mass, okay. So this is also an important point that has been asked in your KCET. Molar mass of protein, polymers and other macromolecules you can determine from the osmotic pressure. Also write it here, KCET question. Okay, KCET previous year question. Right? Okay. Next is what is osmotic pressure? This is what is reverse osmosis. Firstly, let us talk about reverse osmosis. Reverse osmosis is basically when you apply the external pressure here, right, to stop the osmosis. When you apply the external pressure to stop the osmosis. When you can stop the osmosis if the pressure is greater than the external pressure. That is called the reverse osmosis. Now we will see this with the help of a diagram, right? Reverse osmosis. Wait a second. Yes. Reverse osmosis. I am drawing this diagram here, right? This is the diagram as you can see. Here what we are doing, we are applying the external pressure P, right? Now guys, very simple thing. First you tell me, in osmosis what used to happen? In osmosis what used to happen? Solvent particle was moving from lower to higher and solute was moving from higher to lower. Now reverse means opposite of that. Now solvent will be moving from higher to lower and solute will be moving from lower to higher. This is called reverse osmosis. That means what you will observe here, this is your semi-permeable membrane. This is fresh water. This is basically used in desalination of water, right? This is the semi-permeable membrane. I'll just write it here. This is SPM, semi-permeable membrane, right? So in semi-permeable membrane, what you will observe here, that the salt water, firstly in the salt water, what you know, that in the salt water, solvent concentration is definitely low because this is a solution. Solute in a solution, see, if you talk about a fresh water, that is pure. So this is a pure solvent. In pure solvent, this is pure solvent. In pure solvent, can I say solvent concentration is more? Solvent concentration, because there is no solute particles and solute concentration is low, right? Opposite will be there in this case, that here because you have NaCl also, that is why solvent concentration is low and solute concentration is high, right? Okay. Right, it is high. Now, I told you that solvent will move from high to low concentration. High to low concentration means high is this, low is this. That means solvent, the water will move to this direction. Solute particle will move from high to low concentration. Wait a minute, this is the high concentration of solute. Sorry, solute will move from low to high concentration, right? Yes. Solute will move from low to high concentration. That means NaCl will move from this direction to this direction, right? This is the movement of NaCl. But the solvent particle, that means this will move from low concentration to high. That means water will move from this side to this side. That means this is the direction of water. This is the direction of water. This is the direction of water. That means when you have a water that is having, for example, ocean water which is having salt also. So how you will extract salt from there, then get the fresh water? Because in reverse osmosis, the water is moving in this direction. Here, if this water has any salt, it will move in this direction. So here in this chamber, you will be left with salt. In this chamber, you will be left with fresh water, pure water. This is used for purification of water, or you can say desalination of water. And from here only you have the term that is RO, right? RO that we use in our homes, right? To get pure water, right? Okay. Now, always remember this applied pressure is always greater than, the osmotic pressure, right? Next Next is abnormal molar mass and normal molar mass. But before that, we forgot to tell you one thing here. That is three kind of solutions you have: isotonic, hypertonic, hypotonic. Isotonic is when two solutions, we are comparing two solutions. If their osmotic pressure is same, that is called isotonic solution. Okay, that is called isotonic solution. Hypotonic solution is when lower osmotic pressure than the other. The one hypo means very sweet. Hyper means very angry, right? So the one which is angry having high osmotic pressure than the other, right? The one which is sweet is having lower osmotic pressure than the other, right? So if I compare pi 1 and pi 2, this is your hypertonic, this is hypertonic, and this is hypotonic, and this is hypotonic. Right, people who eat salty food, now that's why it is advised that you should definitely eat salt, because that is required for your sodium potassium pump in your body, but that should also be not that much. What will happen if you eat too much of salty food? They experience water retention in the tissues and intercellular space, resulting in edema, right? So that is why salt is necessary, but too much of salt, some people eat too much of salt, right? So that is not appreciable, right? Next is this we have done is applied to the solution side. Pure solvent, it is used in desalination of water, that we have done, right? Next is abnormal and normal molar mass, right? Okay, let's talk about abnormal and normal molar mass. So abnormal molar mass, what is abnormal molar mass, everyone? What is abnormal? This is basically due to association and dissociation. We know two things. If there is dissociation, for example, NaCl is getting dissociated into Na positive and Cl negative, right? MgCl2, it is getting dissociated in Mg2 positive and 2Cl negative. Now, in my assumption, if I talk about the molar concentration, molar mass, I am talking about 1 mole. It doesn't matter which molecule I am talking about. For example, this is my beaker. This is the beaker. This is the beaker that we have. This is the beaker. And in this beaker, what we have is, this is your 1 mole, molecule I am talking about. Right? Now, I know if there is no dissociation, I'll count 1 mole here and that will be my molar mass. But if there is dissociation, some particles will get dissociated. They will get dissociated like this, to smaller units, to smaller units, to smaller units. What will happen? Now, my 6.022 into 10 raised to power 23 particles will be very different. That means they will not include all the MgCl2. They will include some Mg2 positive ions also, some Cl negative ions also. Right? That is how the molar mass will vary. I'll teach you one more way here. We were assuming that in 1 mole you should have, if I talk about this NaCl only, we were assuming that in 1 mole you should have Avogadro's number of NaCl. Avogadro's number of NaCl. But in reality, you got Avogadro's number of Na positive ions and Cl negative ions. Maybe you got Na by 2, half of Avogadro's number of Na positive ions and half of Avogadro's number of Cl negative ions. Understood? Now this will together make Na ions here. That means if I talk about this in 1, 2, 3, 4, so what you will see here, for example, I had 2 molecules here. Just assuming that we had 2 molecules here, right? We had 2 molecules. I was talking about the mass of 2 molecules. But now, here 2 particles means 2 NaCl. But in this case, 2 particles means 1 Na positive and 1 Cl negative, and 1 Cl negative. We were talking about particles only, right? We were not talking about which kind of particle. So here we were talking about 2 NaCl. If we don't assume dissociation, in that case 2 particles means 2 NaCl. It means 2 Na positive and 2 Cl negative, right? But if you talk about 2 particles after dissociation, that means 1 Na positive, 1 Cl negative. That means if we are not assuming that there is dissociation happening, then we must be doing something wrong here. If there is dissociation, the 1 mole particles will be different. Here 1 mole will be 6.022 into 10 raised to 23 NaCl. Here 1 mole will be 6.022 into 10 raised to 23 Na positive and Cl negative ions. So molar mass will also variate. That is called abnormal molar mass. We were supposed to have this molar mass, 2 molecules means molar mass of 2 NaCl, but we are getting molar mass of 1 Na and 1 Cl. Why? Because of dissociation. Right? So if dissociation and association, molar mass from colligative properties is different than the expected value. This is the expected, this is the real. Now what about association now? Association means, for example, CH3COH is forming a dimer, right? It is forming a dimer like this. Now, in our assumption, the molar mass must be Avogadro's number of CH3COOH. But in reality, the molar mass will be for 2 into Avogadro's number particles. So basically I am just telling you 1 and 2 here. I'll just tell you with the help of 1 and 2 here. So for example, you are talking about 2 particles. 2 particles means 2 CH3COOH. Here you are talking about 2 particles. Here 2 particles will be 2 into CH3COOH twice. That means it is total 4 CH3COH. Now here what you can see, that we were assuming molar mass of only 2 particles, but because of the dimerization, when we calculate for 1 mole particles, unintentionally we will get more molar mass here because of dimerization. That 1 molecule is not 1 molecule, it is actually 2 molecules combined together, right? That is why this is called abnormal molar mass, right? Because of association and dissociation, right? That is why we have a factor, because association dissociation can happen anywhere if it is an electrolyte. That's why our colligative property formula will also change. That will change. The factor is Van Hoff factor. It is ratio of experimental value of colligative property to the calculated value of colligative property. That means normal molar mass divided by abnormal molar mass. Observed colligative property by calculated colligative property. This is what you will observe in the experiment. This is what you will calculate, right? This is what you will calculate, that okay, this means this was your observed, this was your observed, this was your calculated, right? Okay, so this is Van Hoff factor, and a very important formula of Van Hoff factor is Van Hoff factor. See, if you talk about NaCl, see, if you talk about HCl, that is having 100% dissociation, right? So in that case, though, you will take, see, if you are having 100% dissociation, I am writing it here. If 100% dissociation, if 100% dissociation is present here, in that case, what we will write, if 100% dissociation is present, alpha is 1. In that case, alpha is 1 is equals to I minus 1 by N minus 1. I minus 1 multiplied by N minus 1, this will cancel. I, Van Hoff factor is equals to N only. What is N? N means, what is N? N means number of particles after dissociation. After dissociation, how many number of particles you will have? Okay, I'll just write it again. Number of particles after dissociation. Okay. Now, if you talk about this thing here, This is if alpha is not equals to 1, there is no 100% dissociation. Then alpha is equals to I minus 1, n minus 1, where n is the number of particles. Just take an example. If you talk about 100% dissociation, for example, HCl, right? This is having 100% dissociation. When you don't have 100% dissociation, for example, CH3COH. For example, they have given you alpha is 50% dissociation. Then alpha will be 1 by 2. So you'll put the value here. You'll put the value here. We know that how many number of molecules it will give us. It will give us CH3COO negative plus H positive. So N will be equals to 2. Right. So here what you will write. This will be alpha is equals to. Alpha is 1 by 2. This is I minus 1. And this will be equals to 2 minus 1. This will be I minus 1 is half. So I will be equals to 1 plus 1 by 2. That is 3 by 2. That will become the value of von Hoff factor. Right? Okay. So it depends. What is the electrolyte what is given to you? If for example they have given you MgCl2. In this case N will be equals to 3. Right? Okay. How many molecules it will give after dissociation? For association, guys, the same thing. If you have 100% association, right, that means all the molecules are getting associated. Association is 100%. Alpha is equals to 1. In this case, it will be 1 is equals to I minus 1, 1 by n minus 1. So it will be equals to I is minus 1, 1 by n minus 1. It will cancel out. I will be equals to 1 by n. I will be equals to 1 by n. That means if I am talking about a dimer, if mostly they will talk about dimer or trimer. Dimer is one molecule, two molecules are combining together. Here I will be equals to half. Here I will be equals to half because two molecules are combining together. Trimer is when three molecules are combining together. So I will be equals to 1 by 3. Right? Okay. So here n is basically number of particles, number of molecules combined together, forming dimer, or you can say forming. Just you can say combined together, right? Combined, number of molecules combined. For example, CH3COOH, it will give rise to CH3COOH dimer, right? Okay, so here if they say this is having 100% association, see, in that case it will depend, right? So what percentage of association they have given us, you will use this formula and you will get the answer for I here, right? Okay. Next guys, how because of this I factor, and one more thing, I is always less for association, I is always greater for dissociation, right? Now based on this I, how our formulas have changed. As you can see here, these are the new formulas that we have after we have changed after we take for electrolytes, right? Just write it for electrolytes. Okay. Why? Because for non-electrolytes like glucose, sucrose, urea, it will have, I want how factor will be unity only, right? For non-electrolytes like urea, sucrose, glucose, non-electrolytes, bond how factor will be unity only, right? Now let us do some questions here, right? Your previous year question, last 3 to 4 years previous year question, so that you can get an idea what kind of questions they can ask you, right? And how I have completed everything here. The swelling in feet and ankles of an aged person, if person is aged, due to sitting continuously for long hours due to travel, during travel, is reduced by soaking. So this is a very old method. Ask your parents when your feet are very swelled up, what they will tell you? They will tell you just soak your feet in warm water. That will help a lot. Why? Because our ancestors were also very scientifically educated. Surprisingly, our ancestors were like way more ahead of these Britishers, right? Isn't it? Now, Why this thing is told to us? Because of osmosis. Now what will happen? The particles, that is why your tissues are swelled up. Your tissues are swelled up because of the solvent concentration is very high there, right? Okay, that is the reason it will move out of your body, and your feet will get relaxation because of that, right? So answer is B, osmosis is the correct answer. The sample of water is found to contain, now this is a numerical based question. Here they are saying that the sample of water is found to contain 5.85% of AB and 9 this is a very important question, okay? Two solutions they have given you, one is AB, one is XY2, right? Here they have given you, they have added both a sample of water is found to contain this much of AB and this much of, these are two solutes. Means here this is not binary solution, this is ternary solution, where this is also the solute, this is also the solute, right? This is a very important question. Here they are assuming the molar mass of this is 58.5 and the molar mass of this is 95. Molar mass of XY2 is 95, right? Now the concentration is weight, sample of water is found to contain this much weight by weight. Weight by weight concentration, guys. So it is having how much weight by weight concentration? It is having how much weight by weight concentration? Weight by weight concentration is 5.85% weight by weight. You can say that weight of solvent, weight of AB is 5.85, right? Weight of solvent, weight of water I will assume to be 100 grams. 100 grams. Okay, here it is weight of weight of not water, weight of solution will be 100. Weight of solution, this is a very important thing that I am going to write it here, right? Very important thing I am writing. Now here if they are saying it is 9.5% weight by weight, that means weight by weight means weight of this solvent or weight of this solute, that is XY2 is 9.5 grams, and total solution of 100 grams, weight of solution is 100 grams. Now guys, see, you have a solution where you are adding two solutes AB and XY2, and the other is XY2. So that means when you calculate the weight of solvent, that means weight of water, it will take weight of water, that means solvent will be equals to solution minus solute. Solution is 100. What is solute? Everybody, what is solute? Solute is, wait a minute, solute is, everybody in the chat box, everybody in the comment section also write it down. 100 minus, everybody, I want you to guys to write it down in the comment section. Pause this and then write it. 100 minus this and this. So it will be 5.85 and 9.5. Right? That means 100 minus 5.85 minus 9.5 will become the mass of water, the weight of water. They are asking you the freezing point. Once you have done this, it will be very easy to calculate all the other things. Right? Now, let us see. Firstly, we will calculate the molality of solution AB. That is, what is molality? Molality is weight of solute divided by molar mass of solute. Weight of solvent, this is 1000. Right? Now, we know that weight of solvent is 84.65. After calculating, it will be 84.65. Calculate this, it will become 84. Wait a minute. Okay, 84.25. Okay, this has become 84.25. Okay, This has become 84.25, sorry, 65. Just write it here, 84.65, right? Now, here you can see, just put the values. What is W2? What is W2? Weight of solute is 5.85. Molar mass is 50. This is M2 given to you, right? This is M2 for this one, right? Now, weight is this, molar mass is this. Solvent has 84.65 multiplied by 1000. That will become the molality of first solution. This is molality of AB. This is molality of XY2. Molality of XY, weight of solution is 9.5. Molar mass is 95. Weight of solvent, this is multiplied by 1000. Right? So solve this, you will get the molality. It is having 1.181. This is also 1.181. Right? Now, if you want to solve the freezing point here, they are giving you the ionization here. For that, see, because degree of ionization is given to you, that means you need to calculate the value of I here, Van Hoff factor here. Here it is 0.8, as you can see from the question. Assuming 80% ionization of AB. 80 by 100 means 0.8 and 60 by 100 means 0.6. That means this is the value of alpha that is given to you, right? So just put the values. We know that AB is giving us to A and B, right? A positive and B. XY2, right? XY2 only, right? It is XY2 only. Wait a minute. It is XY2. Yes. XY2 is giving us 3 ions. That is X2 positive plus 2Y negative. So here the value of N is, here the value of N is 2. Here the value of N is 3, right? So if you put the value of N as 2 here, it is 2 minus 1.8, that is the value of alpha. Put the value here, put the value here, put the value here. This is for AB, this you can write, this is for AB. You can just write it here, this is for AB, this is for XY2, this is for AB, and this is for XY2. This is for XY2. Here I will come out to be 1.8, here it is 2.2, right? Okay, now how to put it in the formula? We know that delta TF is equals to IKF into molality. Molality we have calculated. We know that molality and I are different here, so it will be KF is common. KF is because KF is for water, no, so that is the common thing. I into M1, I1 M1 plus I2 M2. I2 M2. Right, this is your I1, this is your I2. Right, so just put it here. I1 value is this, M1 value is this, I2 value is this, M1 value is this. This is for AB, this is for XY2. This is for XY2 because now both are acting as solutes. So just add it. Value of KF is given in the question. Value of KF is given in the question. They have also told you the freezing point of pure water is this. You need to calculate the freezing point of water sample, right? That means delta TF you have to calculate the value of TF, not TF, delta TF. So delta TF is, we found out to be 8.75. That means this is the value of delta TF, right? What is delta TF? Delta TF is equals to depression in freezing point. That means TF naught minus TF. That means what is the value of TF? TF is 273, I think. It is, sorry, it is not 273. It is 273 obviously. For water, the freezing point is 0 degrees Celsius. That is 273. So 273 minus 8.78. That will become the, wait a minute. Delta TF is given to be 8.78. This is 273 and this is TF. TF will go to this side. It will be 273 minus 8.78 and the answer will be 264.25. Here you will get your answer. Okay. Important question. This is KCET 2023 question. Okay. Very, very important. Right. Next is solubility of gas and liquid. Now they are asking you the solubility of gas and liquid increases with. We know that solubility, gas and liquid, if we increase the temperature, it is going to decrease. Right? Okay. and if we increase the pressure, it is going to increase. Now let us see, decreases with the pressure. No. Increases with temperature, definitely not right. Increases with pressure, increase the pressure, solubility will increase. If we increase the temperature, solubility will decrease. So B will become the correct answer. Okay. Next is, I want you guys to write the answers in the comment section. Okay. The rise in boiling point of the solution containing 1.8 gram of glucose. Now, glucose is your non-electrolyte. That means there is no role of water factor here. This is your W2 because this is your solute. Glucose is definitely solute in what? In solvent. Right? Here they have given you the rise in boiling point is 0.1. That means delta TB they have given you. Right? Rise. That means how much increment is there. Now, weight of solvent is given to be this much of solvent. This is weight of solvent is given. Glucose, we know that the molar mass of glucose is 180, right, gram per mole, right. That too you should know, only on your tips it should be, right. They are asking you the molar elevation constant of the liquid is, right. That means they are asking you the value of Kb. Now guys, we know that delta Tb equals to Kb multiplied by W2 by W1 into M2 multiplied by 1000, right? So if you want to calculate the value of Kb, it will be equals to W1 multiplied by M2 multiplied by delta Tb divided by W2 multiplied by 1000. Now, do we know the value of W1? Yes. Do we know the value of M2? Yes. W2? Yes. 1000, oh, we know only delta TB is also given to us, that is 0.1. Put the values and you will get the value of Kb here. Okay, put all the values, you will get the value of 0.1 is your delta TB, 180. Okay, don't use this formula, right, because you will get confused. Same formula, but I have told you, I have the representation I have given different. That's why you will get confused. That's why I'm saying that. Okay, this is 0.1 into this. You will get 1 Kelvin kilogram per mole as the correct answer. So answer will be A is the correct answer. Okay. Next is Henry's law constant. Now I told you that based on colligative property, based on Henry's law also the question has been asked. Right, Henry law constant for solubility of N2 gas and water. And this is the same question that has Henry law also. This has vapor pressure also. Henry's law constant for solubility of N2 gas and water. Solubility of N2 gas and water is this. KH is given to you. Right, KH is given to you. Then you have the mole fraction of N2 in air. Can you tell me that this which kind of in air means in the vapor phase? So this is YN2 is given to you. YN2 is 0.8, right? The number of moles of N2 in air dissolved in this much of this. Now, if you want to see number of moles of N2 from air dissolved in 10 moles of water. Okay. That means you have 10 moles of water and you need to calculate the moles of air. So if you get the mole fraction of N2, somehow if you get the mole fraction of N2, that is equals to number of moles of N2 divided by number of moles of N2 plus number of moles of H2. We know that number of moles of N2 is very less as compared to H2. In air it is very less, na? N2 is very less. So it will be divided by number of moles of H2 only. Number of moles of N2 we have to calculate, right? For this we need to know two things, mole fraction of N2 multiplied by number of moles of water. Number of moles of water is given to us to be 10. So that means this too we know. Our question is to calculate the value of this. That means mole fraction in. We get the mole fraction in liquid phase. Mole fraction in liquid phase. If we get the value, the mole fraction in the liquid phase, we are already sorted, right? So for that, what we have? We have this is given to us. dissolved in this at this temperature and 2 atmospheric pressure. That means total pressure is given to you. Total pressure is given to you. Right? Okay. Because this Y is given to us. So what is the formula? What is the formula is Y PT. This is YN2. It will give us partial pressure of N2. That means PT we know. PT is given to us as 5. YN2 is given to us as 0.8. So we can easily calculate the value of PN2. Partial pressure of N2. Right? This is so sorted. Now, from partial pressure of N2, how we can calculate the mole fraction? This can we use Henry's law here because they have given us KH also. They have given us KH also. So we know by Henry's law, we know that partial pressure of N2 is equals to KH into mole fraction. KH into mole fraction in liquid state. That means mole fraction in liquid state is equals to PN2 divided by KH. It will be equals to PN2 is given to be 5 into 0.8 divided by KH is 1 into 10 raised to power 5. Right? So this you can get it as, okay, this will be 4 into 10 raised to power minus 5. Right? If you put this thing here, wait a minute, just need to write it here. Mole fraction of N2 you will get it as P of N2 is partial pressure is this much divided by K is 1 into 10 raised to power 5. So it will be 4 into 10 raised to power minus 5. If you put it here, if you put this here, what you will get? Put this here, what you will get? You will get number of moles of N2. You will get the number of moles of N2 as, everybody, number of moles of N2 will be, this is 4 into 10 raised to power minus 5 multiplied by 10. This will be equal to 4 into 10 raised to power minus 4. Yes, we got the answer. That is A is the correct answer. I'm again telling you how to calculate this. See, a very simple method I applied here. Henry, see, you have to see what they have given you. 3 formulas I applied here. They are asking me the value of number of moles of N2. I know mole fraction of N2 is equals to number of moles of N2 divided by number of moles of H2O plus number of moles of N2. Number of moles of N2, because it is a solute, it is very less as compared to H2O. So I will just eliminate N2 and you will get, it is number of moles of N2 is equals to partial pressure of, not partial pressure, the mole fraction of N2 multiplied by number of moles of water. Number of moles of water are already given to me. That's why I got a hint that this formula I can apply. So now I need to calculate the mole fraction of N2. For that I know what is given to me. Mole fraction in liquid phase is given to me and there is only one formula for that. So I just put this formula. I know, I can calculate the partial pressure of N2 from here. Because this is given to me, this is given to me as 5 atmospheric pressure. Now, by Henry's law, if I have this, I have calculated this, I have already this KH here. Now I can calculate the value of mole fraction in liquid phase and put it here, I will get the number of moles of N2. This is again your KCET previous year question, last 2 year only. Right? Okay. Okay, this is how you will get it and answer will be this one. Okay. Next question is, which of the following colligative property can provide molar mass of protein, polymers and colloids with greater precision? As I told you, I even underlined that statement that this is your previous year question KCET, right? So here the answer is osmotic pressure that is going to provide you this thing. Now there is one more question and I want all of you to answer this in the chat box. I want all of you in the comment section. I am waiting for your answers. In the comment section, I am waiting for your answers. I'll give you one hint here. Choose the correct option. KH value is same for gas. Is this same? You can see a table. Higher the value of KH value, more is the solubility. This is the formula. This is Henry's constant. Mole fraction is nothing but it is solubility. right? Mole fraction is nothing but it is solubility. This also I have told you when I was teaching you that how come at a constant pressure KH and solubility are related to each other. They are saying they are directly related. You need to see this from this formula. Are they directly or inversely related? Right? KH value increases on increasing the temperature of the solution. Right? If you increase the temperature of a solution, solubility will decrease. Right? Will KH also increase to make this constant? For this, the hint is you need to make this thing constant. This should be constant. If this thing is increasing, with increasing in temperature, this is decreasing, then it should increase or decrease to make it constant. It's like if you are saying this value is 10, you are multiplying this 2 into 5, or you can say this is 20 equals to 10 into 2. If this value I have decreased to 5, then this value I will increase 5 into 4. Right, this value I have to increase to make it constant. Right, so this you have to tell me in the comment section. Last is easily liquefiable gases usually has lesser KH value. This is definitely wrong. Okay, this I have not taught you. That's why I am already telling you this is wrong. Right, either answer is B or answer is C. Okay, either answer is B or it is C. Now you have to tell me in the comment section whether the answer is B or the answer is C, and I'm waiting for your answers in the comment section. Okay, yes everybody. So guys, that was all about solution chapter. I have completed everything here, included from concentration terms to Henry's law, Raoult's law, ideal non-ideal solutions, colligative properties, everything we have completed, and also along with the previous year questions. Now I want all of you, because a lot of hard work has gone into writing these notes, guys. This was not easy task, right? Okay, this was not an easy task to get the best diagrams for you, write the best notes, and a very simple short notes I have written specially for you. Now if you don't appreciate this thing, then what you will appreciate, right? Okay, so I want to see your lovely comments in the comment section, because that also gives me motivation to even more do better and to give more content to you guys. Okay guys, and bye bye, take care, see you all in the next class. Thank you so much, namaskara.